Hello and good afternoon everyone. My name is Amir Miley and today I'm going to talk about water extent monitoring using satellite imagery, and in this video I'm going to give you a tutorial about how we can extract the water extent using Sentinel-2 imagery. So water extent monitoring is the extraction of water covered area within each image by using spectral indices, which in this case I'm going to use water indices, which each of the water indices have their own equation, which each equation use the spectral bonds within each image, which I will explain to you a little bit later on how we can use these bonds in order to compute our water indices. So water extent monitoring is vital for managing water resources and understanding environmental changes, especially as climate shifts and human activity alter water availability. Traditional methods like ground surveys often fall short in scale and cost. Sentinel-2 imagery, with its high-resolution multispectral data, offers a solution by mapping water across large areas efficiently. Sentinel-2's 10, 20, 60 meter resolution and spectral bands, particularly in the near-infrared, excel at identifying water through various water indices. Research shows it can track floods and seasonal shifts with precision, making it a standout tool for dynamic water mapping. This imagery powers applications like flood response and wetland preservation by pairing with tools like machine learning to refine results despite the obstacles like clouds. Its real-world impact is clear in studies on disaster management and ecosystem tracking, showcasing its value today. Water extent monitoring has several applications such as flood mapping, drought assessment, wetland conservation, reservoir management, climate change studies, and agriculture. So for the purpose of this study, we're going to use images collected from Sentinel-2, which it has high resolution as spatial resolution and precision, which you can easily download it from Copernicus browser from the Copernicus app in here. And Sentinel-2 offers two different packages of data, as you can see here, level 1C and level 2A. The level 1C is a reflection of the top of the atmosphere, and it has radiometric and geometric correction but not the atmospheric correction, which this correction requires to utilize Sentinel algorithm in order to remove atmospheric effects. Level 2A has all the necessary corrections to use in our study, and it's much easier and faster to work with compared to level 1C. So after the selection of our product type here, we use this polygon over here to crop the area of interest. Then we enter the time range that we want, and after entering our time range, we click on this search and some results will be shown in here, and we can easily download our desired product. After downloading our products, we are going to use SNAP or Sentinel application program, which is an open source program used for all kinds of remote sensing studies in order to compute our water indices, and before that we are going to process our images. So before we begin, I'm going to show you something. If you actually downloaded level 1C, you need to come here, thematic land processing and Sentinel processor, and select the version of Sentinel algorithm that you want to use. And if you didn't have this part, you will come through tools here, plugins, and you will have to download it through here. You will easily select this box here and click the install button, which I've already installed it, and it's here, the Sentinel algorithms. So now I'm going to open my product here, which you have to click on this folder, or easily you can drag and drop the product into your workspace, and I'm going to here. So now you can see here my product has been uploaded in the program, and I will illustrate for you. As you can see, there are red, green, blue, and hue, saturation, and value, and I will use the red, green, blue as an issue. And you can see natural colors, false current, infrared, and atmospheric penetration, which each of them use various bonds in order to illustrate the image for you. And I will use the false current, infrared, and as you can see here my image is shown. So at first I'm going to process my image. All of our functions will be done by using this graph builder. First we build our graphs, then we go and upload our graph in batch processing, upload our products, and then we will run the functions in order to achieve the result. So at first, the first graph that I want to build is the processing graph, which it contains two operators. The first one is going to be resampling. I'm coming to here, geometric and resample. The second one is going to be raster and subsetting. These I will explain to you what these operators are later. So let me just connect this one too. After building my graph, I come and save my graph here in the name of processing or whatever name you want. So after saving my graph, I will go through batch processing. I will upload my product here. If you wanted to add individually, you will simply have to select this, but if you wanted to add all the products, you will select this one, which as you can see here my product has been uploaded. And now I will upload my graph here, processing one. So the first operator that we are going to use is resampling. Due to the fact that Sentinel-2 images have bonds with different resolution, which is 10, 20, and 60 meter, resampling ensures all the bonds have the same resolution for a better analysis. As you can see here, we can do the resampling by using the reference band or toggle width and height and pixel resolution. But we are going to use the reference band from the source product here, and I'm going to select level the band B2. And a little bit lower you can see the resampling algorithms that are here. Upsampling method increases the spatial resolution, and downsampling decreases the spatial resolution, and flag downsampling decreases the spatial resolution of flags or masks within the image. And this advanced method, definition by band, you will have to upload a file, and which it contains what to do with each band, upsampling, downsampling, with each of their techniques. In here you will select the general method. So I will let it be just like this, and I will go to subset. Subset separate my region of interest from the rest of the parts and within the image, so that in further analysis my computations will be much easier and faster. And I can cut my area of interest by adding the pixel coordinations here, or I can enter the geographic coordinates, which first I will show you how to extract the geographic coordinations here. So my area of interest is here, and I will select a polygon here. Will drag it out my area of interest, and then I will select this one and select, right click on it, and WKT or well-known text from geometry, I will click on that and extract this coordination. Control C to copy this coordinate, and then OK. I will close my image, and then I will upload my coordinates here. Control V and update. and as you can see here, my area of interest is shown by this yellow rectangle. So I can easily separate the bonds that I want to use in order to reduce the amount of the function by time. I mean, if you let it be like this, it will take much more time than if you separate it with only the bounds that you want to compute in your further analysis. So in here I will use band 2, band 3, band 4, band 8, and band 11 and band 12. So, and I'm finished with it. I'll go to write, and as you can see here, my result will be saved, and in whichever folder I can select it easily, process, and here. And as you can see, this BEAMDIMAP is the format of the SNAP files, and since I'm going to use ArcGIS Pro in this program as somehow a side project, I will need GeoTIFF format as well, but not now, not the process image. So for now I will simply use the BEAMDIMAP. So I will run my processing here. As you can see here, it also shows the duration of my processing. So I will close this. I will leave it just this one. So now I will close the main product here. No, I will open my image. So as you can see, the methods that are used in order to illustrate the image are a little bit more. I would set the land border, which would use band 8, band 11, band 4. As you can see here, it shows the places that contain water or land. So the second graph and part that we are going to use is the water indices, or the part that we calculate the water indices for our image. I will use 1 band merge and 3 band maths here. So I will explain to you a little bit further. Just connect these to read to each of the band math, and since each of these band math will create an individual image, I will use band merge in order to merge all the images that are created from each of the band math into one, so I can easily use them in my further analysis better. So band math is used in order to perform mathematical operations on the bands, and band merge is simply each of the band math will create an image containing the result of each index, and it simply combines all the images. So my first operator here, band math, is going to be my first water index is going to be NDWI, or normalized different water index, which is simple and practical, but it can be affected by soil moisture and built up areas, which they can create false positives. So I will put NaN, or no data value, here, because 0 itself is a value and it might create some false results. And I will enter the equation of NDWI in here. It's band 3 minus band 8, and band 3 plus band 8. So my first water index is NDWI with this equation. So my second is going to be MNDWI, or modified normalized different water index. I will same again, at NaN. Now I will add the expression here, which it used band 3 and band 11. MNDWI is a little bit more complex than NDWI, but it reduces false values and it's practical in complex environments. So I'm going to use band 3 and band 11 in this one. And 11. So this is my second index, and the third one is going to be AWEI, sorry, SH, again NAN. So AWEISH, or automated water extraction index, separates water from shadow, but it's more complex to calculate compared to other indices. So I will show you the equation here. Use band 2 plus 2.5 band 3 minus 1.5 band 8 plus band 11 minus 25 and band 12. So this is the equation of AWEI. So as you can see here, it combines each of the images that are created by NDWI, MNDWI, and AWEI. So I will save this as well as the water indices here. No, sorry, simply save it here. So now I'm going to batch processing, upload my folder, go to our index, this one, yeah. So you can see each of the equations and water indexes. So if you want to do the ArcGIS Pro part, you will need to extract one geotiff here, or you can create each of the images separately, like one image for NDWI, one for MNDWI, and one for AWEI. Doesn't make a difference, but simply you will have to go through this part and you will have to save with geotiff format. So for now I will select this one, since I have a lot of work with in this program SNAP. I will go through one here and I will close this file. Now I will show you the results here. You can see this is the result combining all three indices, and this is each of the images separately. Go to Windows, tile evenly, and here, as you can see, it shows each of the results. This is AWEI, MNDWI, and NDWI, and this is the combination of all three indices. So the second part that we are going to do in this program is going to be, first I need to open all these. I'll reopen this one here. I'll go through Mask Manager here in order to create a mask that it's on my water extent. So I'm going to calculate two water masks in here. First one is going to be lower band, and the second one is going to be upper band. The lower band calculates the intersection of all three computed water indices, which it actually shows where is water 100%. For sure, you know there is water. You will simply need to calculate this lower band. But upper band is the part that each of the indices separately calculated that water index, so you are not sure whether it's that water or it might be something else, like soil moisture or something else. So the first bond that I'm going to create is going to be lower bond, which I will use if NDW NDWI, which are greater or equal to 0, I want to extract the parts that are actually water, and MNDWI that are greater or equal to 0, and AWEIsh that are greater or equal to 0. Close the parenthesis, and here we'll have then go with 1, and or else go with 0. Here, as you can see, it created the place, it shows the place or pixels that are actually water, and others might be soil moisture, or they have weak reflectance. And now since this was my lower, and I'm going to calculate my upper band as well here. Well, I can simply go through here, copy this one, come back and go paste, and I have to just change this and to or in order to create the union of all three indices. So I will use or and or. The rest of the equation is the same. Or. And here I show you the it's a little bit more, have more area than the lower bound. Now upper. And if I go and calculate my masks, which I can do it in here, raster, mask area, lower, as you can see 2.8 square kilometers, and for the other one is going to be a little bit more, 3, yeah, well, almost 3.5, but it's more square kilometers here. And besides of that, I can calculate the statistics of my image, which are here. Sorry, I need to refresh this one, I guess. Yep. And as you can see, it shows some statistical measurements that are here, mean, sigma, median, and others, and it shows the histogram, both PDF and CDF for both bands. And I can easily draw other plots for my image as well, scatter, histogram, and other ones. So we are actually finished with the SNAP program, and I'm going to explain how we can extract the the border of my water extent in the ArcGIS Pro program. So I'll close this one, and I will open the ArcGIS Pro, and I will upload the GeoTIFF format that I've already extracted from the SNAP program. And if you wanted to analyze the lower and upper band, you will simply have to first calculate all the water indices, and then build another graph and crop that union part, go with band math, and enter the equation of lower or upper band and save it with the GeoTIFF format. Or if you wanted to do it individually, you will simply need to create a band math for each water index and then save it with the GeoTIFF program. Well, for an additional note, the calculation of the borderline in the ArcGIS program for the lower and upper band is a little bit easier compared to each of the water indices, since you have already separated the parts that are actually water and non-water. As you can see here, I've already cropped the part that are 1 and 0. I mean, the rest are just no data value. So, but for each of the water indices, since they are not divided into two categories. It's a little bit more tricky, but it's not that much hard. So well, in order to you extract the water extent border in the ArcGIS program, I've uploaded my GOT format image in the ArcGIS Pro, and as you can see here, it shows the values that are between 0.7 till minus 0.7 or 8. Yeah, here. So the first thing, or for the first operation that I'm going to use, is going to be here, analysis tools. It's going to be reclassify. If I had those lower or upper bands, simply I had to use the int or integer in order to convert the values of the image in int. Then I will simply go and turn the raster to polygon and polygon to line. Otherwise, if you wanted to calculate for each of the water indices, first you have to come to classify here, and I will enter my image into the reclassify operator here. It by default enters the value column into reclass field, and for the reclassification you can either manually enter the ranges of the water index, or you can classify it with the computer. You simply need to add the number of classes, and I will select this one, which is much easier to do with this one, and I would go the result will be shown, and as you can see, it divides the image into two sections. The first section is which data are the places that are not water, and the second place, or the purple ones, are actual water. So the second operator that I'm going to use is going to be raster to polygon. I'm going to convert my raster format to polygon here. As you can see, it converted, and the second one is going to be polygon to line. And if you wanted to have a final result, you can use smooth to line operator as well, which it will give you a final result, but it's not that much difference than the result and the extracted from the polygon to line. Yeah, so here I'm done with this, and I will go to symbology here, and I would click the unique values, refresh once to left fit. Left fit is the place that my actual data are. Simply I will put no color for these, since I'm not going to use them and they are not important and they don't interfere with the result. And as you can see here, I'll put some color. And about line width here, if you have simply 1 year, I guess 1.1 is enough. But if you have more years, in order to actually understand how water extent is shifted from year to year, it is better to reduce this line width into lesser amounts, like 0.1 or 0.2 is much better. For the purpose of this video, I simply use one image. As you can see here, the results are pretty good. But if you calculate and for many years, 4, 5, 6, 1 point is more than it's more, and the result will be not fine as you imagine. As you can see here for the image, like, let me show you better. This was for 8 years, and the line width is about 0.1, as you can see here, I can easily determine how shifts happened in each year. But if there was 0.1 line for line width for each of the years, and the result would be much messier, and I couldn't easily determine the shifts between each year. So this was it. I hope you guys use this tutorial, and I wish you a wonderful weekend. Thank you for the watching.